Okay, so then I would like to introduce the second keynote speaker of the day. So Professor Lionel Briand is the Tier 1 Canada Research Chair in Intelligent Software Dependability and Compliance at the University of Ottawa in Canada. He has also a shared appointment as Director of Lero, the Irish National Centre for Software Research. So Dr. Briand is an IEEE Fellow, an ACM Fellow, and a Fellow of the Academy of Science of the Royal Society of Canada. He has won many notable awards and recognitions, including the ACM SIGSOFT Outstanding Research Award and the IEEE Computer Society Harlan Mills Award. So please join me in welcoming Dr. Briand.
So I would like to thank you for your kind invitation and introduction. Thank you very much. I've had a really good time at this conference, actually. Very informative and enriching. So I'll provide my perspective on large language models and test automation. As I was just introduced, I have for now a double affiliation in Canada and in Ireland, but on both sides, I work on AI for software engineering, mostly test automation and requirements quality assurance, and software engineering for AI, mostly how to ensure the safety, security of AI-enabled systems. And in both cases, I work very closely with industry in order to ensure that I have well-defined problems and solutions that account for practical constraints and scalability issues. Before moving and presenting recent projects from which I will try to draw insights, I'd like just to give a brief introduction. Many speakers yesterday have already reminded you about the principles of large language models, the pitfalls of large language models, so I'm not going to do that again. But I want to give you a brief introduction from a testing perspective before moving on to projects. So large language models, we know what they are, but when we want to use them, we have to ask ourselves key questions in a software testing context. For each software testing problem, we need to understand what is the best way to train them, what architecture to use, what data is available, what objective we try to achieve, and how to apply them in practice. You know, you have heard of zero-shot prompting, fine-tuning, few-shot prompting, and what is the best solution very often is, as you will see on my project examples, is very specific to the problem you are tackling and the context in which you are tackling the problem. What data you have access to, for example. So there is no general answer to those questions, even within the scope of test automation. It has to be investigated. What are the motivations for using LLMs for software test automation? There are several. Identifying and designing test scenarios or test specifications, for example. Test data generation, or even automated test infrastructure building, but also test evolution and repair as the system is changing, and test minimization. Today, I will provide you with 3 project examples that cover the topics in blue on that slide. So, when you're trying to use large language models with testing, you are usually trying to build a prompt for your LLM, and that prompt contains information, for example, context information about the system under test, such as parts of its source code, the requirements you're trying to achieve, also bug reports. So what information you provide in that prompt depends, of course, on the specific testing problem you're trying to tackle, and the constraints you have and what type of data you have access to. And then the LLM is used to either repair or generate a test case. The solution may not be satisfactory. Information may be extracted to augment the prompt and iteratively achieve what you're trying to achieve. If I take an example of a prompt, let's assume you are trying to just identify test scenarios in natural language for a booking system, and you are using a future prompting, which means prompting with examples. So the prompt may say, you know, please test a booking system that focuses on the risk around booking dates, and the output should follow a certain format. And then you provide examples, which is a future prompting, a couple of examples below. And then you may obtain an output that gives you the 3 test scenarios that you asked for. So that's a simple example of a prompt. And here we can see already many of the elements of the prompts. The fact that you are providing instructions, you are giving some context information, you are giving training examples, you are indicating what should be the format of the output, and all those things can be part of a prompt for testing. So for testing, instruction may be simply guidance to generate test inputs. The context may include parts of the code under test. The input data may be requirements, and so on. You can fine-tune those models as well, which is also an alternative. But of course, there are limitations to fine-tuning. For certain type of problems, it's actually difficult to have enough data in sufficient amount to fine-tune, especially extremely large models with many parameters. Those models, of course, are then only usable for very specific tasks, which means that in practice, you have to maintain possibly a large number of fine-tuned models, which is, comes with a cost. And of course, you have the usual problem of overfitting. So fine-tuning is not always, again, in any context, the most practical option. So if you look at the literature on LLMs and testing, if I summarize the challenges, the test quality, or the quality of the generated test cases, for example, depends and is very sensitive to the prompt, how you design prompts. And that's a bit of a problem. Many test cases that are generated are typically, according to many studies, not executable. Often they achieve low coverage, but the results in the literature are quite inconsistent. There is usually no good solution for the test oracle, which means that it's okay, it's a good thing to generate many test cases, but if you don't have a test oracle, that defeats the purpose of test automation. So, and LLMs so far do not really provide a solution for that problem. And of course, whether LLMs work well depends a lot on the domain of the software under test. It has a significant impact on the quality of the LLM output. If you are testing web systems, you can probably do a good job. If you are testing an embedded system on a satellite, I'm not sure the LLM in its training has seen a lot of that in the course of its training. So the results are not consistent across domains. Of course, as we will see, some of those problems can be addressed. There are potential solutions to consider and investigate. We have also seen that in the previous talk. And I'll get back to that. But for now, enough with the introduction. And let's look at some recent projects and try to gain insights from that. So I will only present projects that were completed recently and that are published on arXiv and under review. So, except for the first one. One problem that I've mentioned is test design. That is, identifying and designing test scenarios in a systematic way, for example, from requirements, in order to avoid biases and blind spots. And very often in many domains, safety-critical domains and mission-critical domains, industry standards require traceability between requirements and system tests in order for the system to be deployed or even for the system to be accepted by customers. And one project in the automotive domain that I did some years ago was about that. Basically, our partner had requirements expressed as use case specifications and had, it was in Europe, and had a testing team in China. And the point was to be able to demonstrate compliance of the system with requirements written as test use case specifications. And those are quite common in many industries, but it was a very manual and laborious task, and an error-prone task as well. And what we did at that time, around 2018, it was before LLMs could be used, we used advanced NLP and developed a technique called UMTG that I will introduce briefly. And at a high level, UMTG takes use case specification in input, but unfortunately, this wasn't enough to enable full automation. And we had to do some lightweight modeling. We had to model the domain of the system, that is, model the concepts used in use case specifications, and some of the conditions appearing in the use case specification in some analyzable form. And of course, it worked, but that was a practical impediment to ask people to do that lightweight modeling. Moreover, we couldn't use just random use case specifications. We needed to follow a methodology that was analyzable using natural language processing. And of course, if people write use case specification in a completely free form, this becomes difficult. So we had to resort to something called restricted use case modeling, which is a restricted way of writing use cases so that every step in the use case specification can be interpreted in an unambiguous manner by a natural language processing algorithm. And again, that was a practical constraint. And of course, we had tooling to ensure compliance and to help engineers, but nevertheless, there was a practical constraint. And then the question I have, and I'd like to investigate, and I've started to investigate, is whether using LLMs instead of advanced natural language processing could help avoid entirely or partly any form of lightweight modeling and constraint description. And whether it could help avoid also the requirement that we have that people write use case specification in a precise and structured way. And so I think LLMs have a significant potential to bridge the gap between requirements engineering and testing. But of course, again, the result, because LLMs are trained on data from the internet, and we don't always know the sources of that data, the results may depend on the domain. Another project, a very recent project, available on archive, is about test evolution. As you know, most systems undergo frequent system updates. They have large system test suites. It's not unusual to have system test suite of thousands of test cases. Maintaining the quality of the test suite is extremely expensive as the system is evolving. At least that's what our industry partners are telling us. But on the other hand, you have to maintain those test suites. It's extremely important for quality assurance purposes. You cannot have test suites that are written with obsolete test cases that fail for no reason. And then the question is, can we somehow support automated test case evolution? Is this possible? Using LLMs, of course, in this case. So we developed a technique called Target. And basically, there are two steps. One where we build a repair context and prioritize it. The context is basically broken down into two sources of information: the test context, that is what is the broken test code, and the repair context, that is what are the code changes in the SUT that are relevant for that repair. So we extract that information somehow, we prioritize it, because usually, as you will see, we use models that have a limited context window. I mean, in fact, as you will see, we use models that are not too large for practical reasons that I will mention. And we use an LLM then to generate a repair. And that LLM is fine-tuned. And because it is fine-tuned, with data that is expensive, you need, basically for that problem, you need broken test cases, information about broken test cases. And, there are limits to how much information you can collect within a certain cost for fine-tuning. So what we did is that we selected models not only that were open source, and they were pre-trained on code for obvious reasons, but also that has a size under 1 billion to increase applicability in terms of fine-tuning in our context. And we selected the one that had the highest performance on human eval, the well-known benchmark that was mentioned yesterday. And I'm not going to go through the details of the results because I'm covering 3 projects in an overview. But basically, we achieved pretty interesting results in terms of test repair. Not perfect, because you cannot expect perfect results from LLMs, but pretty good. For example, 80% code bleu, which is a well-known similarity measure, when we compare the ground truth, that is a correct test case, with the repaired test case, and also a 66% exact match accuracy. Now, the question, of course, is that we know that LLMs are never going to be perfect. They're never going to provide perfect solutions to those complicated problems. But what is important is, can we understand, can we even predict when we can trust the answer, the output, or not? Because if we know when we can trust it, then we can use imperfect solutions. Because the engineers may decide to use the output, in that case to use a repair, or ignore it without waste of time. And so we build a model, a machine learning model based on random forest and using features about the similarity between the inputs test context and the repair context. Also looking at the complexity of the changes in the SUT, the complexity of the test code. And based on that, we're able to very accurately predict when to trust the repair or when not to trust it. And that type of predictive trust model is extremely important when you use LLMs. And I'll get back to that, in order to make them usable in practice. Unfortunately, of course, building such a trust model, how you do it is very dependent on the particular problem you are tackling and the context in which you are tackling it. There is no general solution, okay? And also, we were able to show that a target has the capability to generalize across previously unseen projects without getting into further details. The last project I'm going to present before reflecting on the topic is about flakiness, repairing flakiness in test cases. You know what flaky tests are, tests that intermittently pass and fail. Previous studies have shown that 70% of the cases are due to problems in the test code. So that's what I focus on here. And of course, there are many reasons why you should detect and repair flaky tests. Otherwise, you end up wasting a lot of time. And it might hide real bugs in the source code. You might not be able to reproduce failures. I mean, there are many, many reasons why you should try to fix flakiness. So we developed a technique called flaky fix. There are 2 steps, 1 and 2, that I'm going to describe now. The first one is a big predicting the fixed category. And you might ask, why do you need to do this? You want to repair flakiness in a test case. Why do you need to predict the fixed category? And what is the fixed category anyway? And I'm going to tell you why. So for example, one fixed category is that the data structure you have used in your test is inadequate. So that's one test category. For example, you may want a data structure that maintains the order in which the elements are stored, regardless of how many times the code is executed. And so we have a number of categories that I will mention next. But how do we predict the fixed category? given that usually we have a small label data set of flaky test. Again, this is not a problem usually where you have a huge, you can afford to collect a huge data set at a reasonable cost. So we use few-shot learning classifiers, which are basically based on the idea that you somehow measure similarity in a meaningful way, so that you can use similarity to determine whether different, for example, test cases belong to the same class, for example, belong to the same fixed category. In that case, we fine-tuned two code LLMs, Unix Coder and CodeBERT, using Siamese network. Siamese network is a way to project your input vectors into a different space so that, in our case, test cases that belong to the same flaky fixed categories are close together in that space. So that's a technique to enable few-shot learning. The results are pretty good, as you can see here, in terms of average precision and recall. Those are the categories of fixed categories that we have, from change assertion, reset variable, change conditions. I won't go into the definitions of those categories. As you can see at the bottom, there is a category miscellaneous. They are basically flaky tests that we cannot classify. And of course, for those, the precision and recall is pretty bad, because we cannot learn patterns or similarity patterns for a category of miscellaneous test cases. I mean, that's not possible. The second step is when we repair, and here we use a GPT 3.5 Turbo. It's a quite a large model, but we don't have to fine-tune it. We don't fine-tune it, so that's okay. We use the fixed category in input to guide the repair. And you will, of course, you can ask, well, okay, why? You will find out soon why we do that and whether there is any benefit. But we tried two different prompts, one within context learning, that is, we provide examples, and one without it. In fact, we also tried without the fixed category, and you will see what the result is. And then we analyzed those different prompts without the fixed category, with the fixed category, with the fixed category, and the examples for few-shot learning. And first, the results showed very clearly, in terms, for example, of blue score, that the labels of the fixed category help in terms of determining, in terms of providing, a correct repair. And we obtain actually blue scores, if you're familiar with blue scores and what you usually find in the literature, that are actually quite high. Of course, what that means is another question, and I'll get back to it. The second thing is that in-context learning helped as well for 2 out of 3 categories. We couldn't investigate the other categories because we didn't have enough examples to do that. So, based on the results, the flaky, the repair category, and in-context learning was helpful in order to obtain higher blue scores. That is, repair that were more similar to the ground truth. So to conclude, it seems that semi-automated repair of flakiness is possible. We have presented a 2-step process that entails first to predict the fixed category and then to generate an actual fix using LLM with few-shot learning. There is a quite, if you compare to the repair literature, a high similarity degree in terms of the fix and the ground truth. However, the problem with those studies, and not just this one and all the others, is that we don't know what high blue scores really mean. We don't know what that means in terms of benefits for the programmer, for the tester. And of course, not only larger data sets are needed in that case, but also user studies. Last project I want to briefly present is on test minimization. In practice, in large test suites, there are a lot of redundant test cases. And for example, in the context of regression testing, you cannot just test, huge amounts huge numbers of test cases, especially in a continuous integration and development environment with frequent releases. So you need to regularly make sure that you minimize redundancy in your test suites. And that's what test minimization does. And you want to do that and at the same time maintain a high fault detection capability, of course. So we developed a solution. Without going into detail, which is basically black box. It only relies on test code. We tried a number of large language models that are listed on the slide. We looked at similarity between test cases. We used a particular genetic algorithm that was parallelized to identify optimal subsets of test suites. And of course, our goal was to achieve a high fault detection. And we have some interesting results. And also, because scalability is a big problem in test minimization. It has been a problem for 30 years. We were paying attention to how fast we could minimize test suites and how far we could go in terms of the size of the test suites. That was one of the main objectives and actually one of the main motivations to use LLMs, actually. So you can find that paper on arXiv as well, on LTM. So the steps are kind of expected. We extract embeddings, we compute similarity, and we use evolutionary search to identify a minimized test suite. We did some evaluation in terms of minimization time, testing time saving rate, for detection loss. We compared with a baseline that was based on program analysis and building ASTs and comparing similarities between ASTs. And the main problem with that approach was scalability, like I've mentioned. But on the other hand, that's not a new problem with test minimization. And basically, we showed that relying on LLMs, we could run minimization with an order of magnitude faster than the best existing approach, and even achieving a slightly higher fault detection rate. And also, we found out that bigger models were not necessarily better, actually. That's also, I think someone said that yesterday, you have to be careful about that. So now, trying to reflect a little bit on those examples and more. There is a significant body of work already in LLM testing, and there is an excellent survey you can find on arXiv. But despite that significant body of work, there are still a lot of research problems. First, we need to better guide test automation. For example, we need to better guide test generation, whether it's from requirements, from bug reports, in terms of maximizing coverage. Because again, we don't have solutions for the oracle. So if you don't have solutions for the oracle, you need to somehow control the cost of testing by controlling the size of your test suites. And therefore, you need to be very effective in the way you guide a test generation and test selection. And of course, what that means is that we somehow need to intelligently combine LLMs with other techniques, such as meta-heuristic search. You have seen an example in the previous presentation of that. Fuzzing, but also metamorphic testing and other traditional techniques, even symbolic techniques, in combination with LLMs. And you have seen, for example, in the LTM project on minimization I presented before, that we combine LLMs and evolutionary search to achieve test minimization. We need to optimize prompts in terms of effectiveness and cost. There is always a limited context window, especially if you tend to use smaller models, which is often important, as I've shown, in context where you don't have huge amounts of data for fine-tuning, for example. What that means is you need to prioritize and select context information in some effective way in your prompt. And we have seen an example with Target. I didn't go into details, actually, but in Target, we have a quite sophisticated set of heuristics to prioritize context, prioritize changes in the code, and information from the test code that is part of the context. But we need to work on that for every testing problem and every context. Again, there is no general solution for optimizing prompts, okay? Like there is no solution for effectively guiding test automation. It all depends on the objectives of testing, what information you have available, you know, etc. What your objectives are. We have to, in some way, to address the non-determinism, uncertainty of LLMs. For example, you have seen that in Target, we built a trust model to predict whether or not we could trust a repair. But you need to be able to address that in general for every testing problem. Otherwise, you may end up wasting a lot of time, and your LLM-based solution may end up not being practically usable, you know, as a result. Imagine our repair solution without this, where we tell people, well, we have a 66% exact match. Well, too bad, you know, in 34% of the cases, it won't be an exact match. You have to find it out and repair it, if needed. I mean, you know, that's not a practical solution. So this usually needs to be addressed for every testing solution. We also need guidelines for, as a researchers, more from a research standpoint, for designing and running proper empirical evaluations. Right now, we are still at a stage where everybody's doing different things, and you know, many studies have flaws. For example, they don't address data leakage, which is not always a problem, but which may be a problem. You know, stuff like that. So we need somehow, as a research community, to agree on how we investigate those things, what needs to be reported, you know. And beyond metrics, like code bleu or whatever, what you find in many of those papers, we need to go beyond metrics, and we need to better understand the benefits on the user side, and whether they're programmers, testers. But of course, those user studies are very hard to run. That's why you don't find them much in the literature. And of course, the infamous test oracle problem. You know, it's nice to generate test cases, but you know, if you don't have an automated oracle, you know, the benefits of test automation are going to be limited. And there are not that many options, and I can't think of solutions for LLMs alone to be able to address that, except maybe in certain domains where the LLM has been extensively trained on, but I don't know. And so there is maybe some hope in combining LLMs and metamorphic testing, but the question is how to do that effectively. Thank you very much.